A Brief History of Time by Stephen Hawking. Analysis and Summary. Narrated by Saurav Chakraborty. Synopsis. A Brief History of Time is a concise summary of the origins and nature of our universe. Stephen Hawking guides readers through the evolution of our scientific understanding. He starts with Newton's law of gravity in the 1600s right through to the modern theories of the universe's beginning. This book is a clear and understandable guide to the universe. From black holes to time travel, Stephen Hawking explains some of our universe's most essential mysteries. Stephen Hawking's perspective. Stephen Hawking was regarded as one of the most brilliant theoretical physicists in history. His work on the universe's origins and structure, from the Big Bang to black holes, revolutionized the field. Hawking was born in Oxford into a family of doctors. Hawking began his university education at University College, Oxford, in October 1959. He received a first-class BA honors degree in physics. Then, Hawking began his graduate work at Trinity Hall, Cambridge, in October 1962. He obtained his PhD degree in applied mathematics and theoretical physics, specializing in general relativity and cosmology, in March 1966. He was the Lucasian Professor of Mathematics at the University of Cambridge between 1979 and 2009. At age 21, while studying cosmology at the University of Cambridge, he was diagnosed with amyotrophic lateral sclerosis, ALS. Part of his life story was depicted in the 2014 film The Theory of Everything. Theories of the past can predict the future. Stephen Hawking explains to readers that a theory is a model that accurately explains observations within our environment. The most widely accepted theories are supported by consistent findings across several experiments. These theories then explain how and why things happen within our environment. Hawking offers two benefits associated with the development of theories. Theories offer a foundation for scientists to make predictions about future events. Hawking provides the example of Newton's theory of gravity. This theory allowed scientists to predict the future movements of planets. Theories are never fully consolidated. This means they can be continually improved as more evidence surfaces. This disprovable nature is crucial for developing our knowledge. Scientific theories allow us to infer the nature of our future universe. However, it is always evolving and becoming more accurate at predicting the future. Newton's theory of gravity significantly evolved our understanding. Newton's theory of gravity was revolutionary. During the 1600s, people believed that objects were naturally at absolute rest. Hence, without any action, the object would remain stationary. Newton flipped this idea on its head by suggesting that all the universe's objects are in constant motion. This theory was supported by Newton observing the planets continually moving in relation to each other. Newton's three laws. Based on Newton's findings, he developed three laws. All objects will continue moving in a straight line if not acted on by another force. An object will speed up at a rate proportional to the force acting on it. Additionally, the greater the mass of an object, the less a force affects its motion. All bodies in the universe attract other bodies with force proportional to the mass of each object. The speed of light challenges Newton's theory. As we are in constant motion relative to other objects, Newton described speed as relative to other objects. However, Hawking explains that our understanding of the speed of light challenged this part of Newton's theory. The speed of light must always be a constant rather than relative. It is always 186,000 miles per second. The solution to this hole in Newton's theory was solved in the early 20th century by Albert Einstein. Specifically, Einstein's theory of relativity. Time is not fixed. The theory of relativity built upon Newton's theory of gravity by accounting for the speed of light being a constant. Einstein suggested that the laws of science are the same for all freely moving observers. Hence, this accounts for the constancy of the speed of light. No matter the speed of a freely moving observer, the speed of light will be the same. The reasoning behind this principle is that time is relative rather than fixed. Hawking uses an analogy to explain this point. Imagine a flash of light is emitted to two observers. One of these observers is traveling toward the light, while the other is traveling faster in the opposite direction. The speed of the light remains the same for each observer as it is constant. However, time is determined by distance traveled divided by speed. Hence, the two observers would perceive the emitted light at different time points. Crucially, this means that neither observer would be incorrect in their recording of the time when the light was first emitted. Instead, time will be relative and unique to each of the observers. Quantum state helps us measure particles. All matter consists of particles. Therefore, to better understand the universe, we need to understand particles, including how they behave and their speed. Hawking explains that particles are particularly difficult to measure though. The more precisely you try to measure a particle's position, the more uncertain its speed becomes. Similarly, the more precisely you try to measure its speed, the less specific the particle's position becomes. This phenomenon was discovered in the 1920s and is called the uncertainty principle. To overcome the limitations of measuring particles, scientists started to measure the quantum state of the particles. Quantum state combines many likely possible positions and speeds of a particle. Hence, it is currently impossible for a scientist to observe the exact position and velocity of a particle. Instead, scientists have to track all the likely places it could be and determine which of these is most likely. This requires scientists to observe the particles as if they were waves. The variety of positions that a particle can appear in can be plotted as what looks like a continuous, oscillating wave. The most likely positions of the particle arise where arcs and dips conform to one another. Massive objects curving spacetime causes gravity. Hawking explains the gravity of massive objects causes curving spacetime. Additionally, huge masses like our Sun alter spacetime. Imagine the analogy of spacetime as a blanket stretched out and held in the air. Placing an object in the middle of the blanket will cause the blanket to curve and the object to sink. Once this curve is produced, other objects follow these curves in spacetime. Hawking explains this is because an object always traverses the shortest route between 2 points. With larger objects, this is a circular orbit. Spacetime is the fourth dimension within our world. Physicists use spacetime to describe events within the universe. To these scientists, an event occurs at a particular position in space and time. Scientists have to consider time because the theory of relativity states that time is relative. Subsequently, it is an essential factor in describing the nature of an event. Crucially, our understanding of spacetime allowed us to evolve the theory of gravity. Collapsed stars can produce black holes. Stars rely on enormous amounts of energy to produce heat and light. Plus, as they often have a long lifespan, this amount accumulates. Once this energy runs out, the star dies. The size of the star will then determine the product of this star's death. For example, massive stars produce black holes. Hawking outlines why the death of giant stars can produce black holes. Black holes are created from these events as the gravitational pull of massive stars is so strong. Stars use their energy to prevent themselves from collapsing due to the strong gravitational pull. However, once the star has run out of energy, it starts to collapse on itself. All surrounding matter is pulled inward towards an infinitely dense, spherical point called a singularity. This singularity is what we call a black hole. A black hole's pull is so strong that light bends along it. Additionally, its strong gravitational pull prevents anything that crosses a particular boundary around it from escaping again. Hawking notes this point of no return is called the event horizon. Light is the fastest moving thing in the universe. However, even light cannot escape black holes. As light cannot escape black holes, this highlights a dilemma for observing them. However, scientists search for the gravitational effects on the universe and the X-rays produced when the black hole sucks in and tears up matter. Time can only move forwards. Hawking explains in A Brief History of Time that the universe's expansion allows time to move forward. However, several scientists haven't given up on the possibility of the universe beginning to contract and time starting to run backward. Despite this, Hawking argues there are several strong indicators suggesting that time can only move forward. The arrows of time. The second law of thermodynamics is called entropy. Entropy suggests that disorder tends to increase with time. Disorder does not generally become spontaneously reordered, suggesting that time can only move forward. For example, a broken cup will not spontaneously become reordered. This is the thermodynamic arrow of time. Similarly, you will develop a memory of this cup having broken. However, before this event, you would not be able to recall its future position on the floor. This is the psychological arrow of time. Finally, the cosmological arrow of time refers to the universe expanding. As the universe expands, entropy increases. Suppose the disorder in the universe were to reach its maximum point. In that case, the universe could start contracting, reversing the cosmological arrow of time. However, we wouldn't know about it because intelligent beings can only exist as disorder increases. This is because we rely on the process of entropy to break down our food into energy. Subsequently, time might one day move backward. However, we will not be there to see it. The four fundamental forces. Gravity is one of the fundamental forces of the universe. However, Hawking describes three other fundamental forces of the universe. Electromagnetic force. Electromagnetic forces can be observed on all particles with electric charges. This includes electrons and quarks. Also, these forces create events like a magnet sticking to a refrigerator. These forces can be attractive or repulsive. Attraction occurs between positively and negatively charged particles. Conversely, repulsion occurs when two equally charged particles meet. Hawking highlights that this force is far stronger than gravity and impacts even the smallest atoms. Weak nuclear force. Weak nuclear force acts on all particles that make up matter. This force is considered weak as it can only exert force at short distances. Nuclear forces produce radioactivity. At higher energies, the strength of weak nuclear force increases until it matches the electromagnetic force. Strong nuclear force. This nuclear force can bind protons and neutrons in the nucleus of an atom. Similarly, it can bind small quarks within protons and neutrons. Strong nuclear force differs from weak as it gets weaker at higher energies. Grand unification energy. A state of high energy exists called grand unification energy. This state occurs when all three forces reach equal strength. In doing so, they become different aspects of a single force. Hawking suggests this unitary force could have played a significant role in the creation of our universe. How did the Big Bang happen? Scientists are almost entirely in agreement that the Big Bang happened. However, where many scientists disagree is how the Big Bang happened. There are two prominent theories of how the Big Bang could have happened though. The hot Big Bang model. The universe started with zero size and was infinitely hot and dense. The Big Bang produced expansion, which subsequently cooled the temperature of the universe. The reason for this cooling is the temperature is now being spread further. In the first few hours of this expansion, most of the universe's current elements were created. The larger bodies within the universe started to rotate due to gravity, which created galaxies. Clouds of hydrogen and helium gases then started collapsing within these galaxies. This collapsing, associated with a collision of atoms, created nuclear fusion reactions. These reactions were the origin of stars. The death and collapse of these stars created huge stellar explosions that ejected more elements into the universe. These elements helped create more stars and planets. The inflationary model. The energy of the early universe was so high that the strengths of the three forces spoken of above were equal. With universe expansion, these three forces developed different strengths. This occurred rapidly. With the forces splitting in strength, an enormous amount of energy was released. The release of energy created an anti-gravitational effect. The anti-gravitational effect caused the universe to expand even more rapidly. Concluding quote. If there really is a complete unified theory that governs everything, it presumably also determines your actions. But it does so in a way that is impossible to calculate for an organism that is as complicated as a human being. The reason we say that humans have free will is because we can't predict what they will do.